All right, so we were abruptly interrupted by a phone call, which was good because I needed a break. Got myself a glass of water. There are 40 questions, and so conveniently that ended us halfway through, so we can continue on. All right. All right, so explain why the reaction that occurs in the glass tube cannot reach equilibrium. As I was saying before and then was interrupted, this is in a open system. So you cannot reach equilibrium when you are in an open system when that reaction involves gases or vapor. So you can simply say that. It is an open system or it is not a closed system, however you want to explain it. Because we have things leaving the system, we cannot reach equilibrium. The last question, state one change in reaction conditions other than adding a catalyst that would cause the rate of this reaction to increase. So there are a number of different things you can do, but we could increase temperature, we could increase the concentration of our reactant, so that could be either PBO, actually it can't be PBO, scratch that, that is a solid. It would have to be H2. Remember, we can only increase the rate of a reaction by things that are either gaseous or aqueous. Or we could also change the surface area of the PBO. So if we made them smaller pieces, so maybe increase the surface area of the, oops, sorry, I'm again off the screen, of the PBO, okay, of the metal oxide, of the lead 2 oxide. Okay, that's increase surface area. That's what the SA stands for. All right. And then that question is done. All right, again, I'm going to reiterate, you should be reading everything that's up here in the question. Seawater contains dissolved salts in the form of ions. Some of the ions found in seawater are calcium +2, magnesium +2, potassium +1, sodium +1, chlorine negative, hydrogen carbonate negative, and sulfate -2, polyatomic ion. An investigation was conducted to determine the concentration of dissolved salts in seawater at one location. A 300-gram sample of the seawater was placed in an open container. After a week, all the water had evaporated and 10 grams of solid salts remained in the container. To determine the concentration expressed as percent by mass of the dissolved salts in the original sample of the seawater. So on the back of our reference tables, we have some math that's going on here, and so this is right on the back of our reference table to understand what we need to do. So we'll see here for not under concentrations, for percent composition. I'm going to move this and cover up our question here for a second. We have percent composition by mass is the mass of the part over the mass of the whole. They want to know the percent mass of the salt. So we know the mass of the salt based on our question is 10 grams. We know that the sample that they took from the water, which contained not only water but also the salt, is 300 grams. And then we have to multiply that by 100 according to our formula, and that will give us our percentage. And if we do this math, we'll find out that we end up with, and if we use sig figs, it would be 3.3%. So 3.3% would be the correct answer for that. Number 24, at standard pressure, compare the freezing point of seawater to the freezing point of distilled water. This is a colligative properties question. Notice that we don't have to do any calculations. They just want to know what's going to happen to our freezing point and in this solution. So remember that when something is dissolved in water, when a solid is dissolved in water, we have something called freezing point depression and boiling point elevation. Boiling point elevation meaning that the boiling point goes up, elevates. Freezing point depression meaning that the freezing point goes down. So we need to say seawater, because it's the stuff that has something dissolved in it, compared to distilled water, which would be pure water, just H2O. We will say that the seawater has a lower freezing point than distilled water. Okay, And our last question on this page, explain why the evaporation that occurred during the investigation is an endothermic process. So evaporation is part of a phase change that is going from a liquid to a gas. And that's part of a heating curve. So if we take a look at this is our liquid and our gas. And I know that this is boiling, but this process is still the same. It's just at a temperature not at its boiling point. Either way, this is part of a heating curve. And all heating curve things that are going on is always going to be absorbing energy. In order to warm up the water, it's got to absorb energy. In order to get the water to boil, it's got to absorb energy. In order to warm up that gas, it's got to absorb energy. So going from a liquid to a gas simply is going to be absorption of energy. So we can just talk about the heat of vaporization needing to be a positive delta H. We could say that we need energy is needed to overcome the IFAs, the intermolecular forces, or we can say that energy is required to change a liquid to a vapor. But whatever you say, you just have to somehow mention that you need to add energy to a liquid to get it to change to a gas. And so that's what I'm going to write, simply saying that energy is needed to be absorbed in a liquid to convert it to a gas. So something to that nature. All right, and that's that. Okay, question number 26. Question number 26 is in regards to this balance equation. A 1 mole sample of glucose, C6H12O6, completely reacts with oxygen as represented by the balance equation below. Write the empirical formula for glucose. So our glucose is C6H12O6. To get the empirical formula, we have to basically reduce this to the lowest whole number integers. So we look at what factor can divide out evenly, the greatest common factor. So we can divide out a 6 out of all these, which would give us CH2O, and that is your empirical formula for glucose. Using the axes in your answer booklet, also right here, complete the potential energy diagram curve for the reaction of glucose with oxygen. So we do this by looking at the equation, and notice that energy is in there. Now, energy can be in the equation, or it could also be listed as a delta H. If it's a delta H, they're going to give you a positive or negative sign. That positive or negative sign tells you whether or not it's endothermic or exothermic. And you can use your reference tables. You don't have to memorize that part of it. So in our reference tables, down at the bottom this is our table I, heats of reactions at 101.3 kPa and 298 Kelvin. You'll see at the bottom here it says the delta H values are based on molar quantities, blah, blah, blah. A minus sign indicates an exothermic reaction, which means that a positive sign would indicate a endothermic reaction. Okay, well sometimes they don't give us a delta H. Sometimes they just give us the energy in the equation. So we have to understand what that means. Exothermic means that energy is released, or endothermic meaning that energy is absorbed. So when we see energy as a product, that means it's being released. And so this indicates that we have a exothermic reaction because energy is on the products. If the energy showed up on the reactant side, it would be an endothermic reaction. Now, how does that translate to a potential energy diagram? Well, if it's an exothermic reaction, it means that our products have lost some of their stored chemical bond energy, and that chemical bond energy has been released as heat. So we need to, if this is my reactants, we need to show our products being lower. And then we can just connect those with our hill that indicates energy being absorbed and then energy being released. This is bond breaking, bond making. Energy absorbed when we're breaking bonds, energy released when we're making bonds. Some of the things we should know about this that are not asked on this, but we should also know that the difference between the potential energy of our reactants and products is the delta H. Or I should say, actually, it's the potential energy of products minus the potential energy of reactants. We should know that this going from our reactants to our peak is known as our activation energy. We should know that going from our baseline up to our reactants is the potential energy of our reactants. We should know that this from the baseline up to our products is the potential energy of the products. We should know that up here we have something called the activated complex. And if we had a catalyst that was added, we should be able to draw a line that shows the lowering of that activated or activation energy, noticing that I don't change the location of where my reactants or products begin or end. Okay. Question 28. The volume of the NaOH solution is expressed to what number of significant figures? So again, we're going to have to read the question, but let's find our volume of our NaOH solution. It says here after 30 milliliters of 0.15 molar NaOH solution is slowly added to the flask. Okay, so we have 30.0. Again, we have zero rules that we have to worry about. The zeros that are leading have no significance. Zeros that are in the middle or captive zeros always have significance, and zeros at the end only have significance if there is a decimal. And when we say the beginning or in captive or at the end, trailing, we're saying after, for trailing zeros, we're saying after the last 1 through 9 number. The zeros, those are all both considered trailing zeros, and they will count if there's a decimal. Since there is a decimal, we count both of these zeros. So there are 3 sig figs. Okay, complete the equation in your answer booklet for this neutralization reaction by writing the formula of each of the products. So in the answer booklet, they are going to give you, which we don't see here, but this would be listed in your answer booklet. HNO3 plus NaOH goes to, and they'll give you a couple blanks. So this is like a double replacement reaction. Remember that we're making a salt and water. I'm looking at my products here. Okay, we're good. So we're making a salt and water. So it's like a double replacement reaction where basically the hydrogen from our acid and the OH from our base combine together. So we end up flipping our fronts, so the Na flips with my hydrogen, and we end up with NaNO3. That is our salt, a metal and a non-metal, in this case a polyatomic ion, plus HOH, or you could write H2O. Would be fine as well. Number 30, in the spacer answer booklet, show the correct numerical setup for calculating the concentration of HNO3. Okay, so this is a formula that's in our reference tables again. So this is a titration. It tells you titration. If you go into your reference tables on the back where we have formulas, there's a titration formula. So that's what we're going to use. M sub A V sub A is equal to M sub B V sub B. M sub A V sub A is equal to M sub B V sub B. Now, if you look at the reference table, it does tell you that M sub A is molarity of the H plus ions and M sub B is molarity of the OH minus ions. That's kind of significant because if we weren't dealing with a monoprotic acid or a monohydroxy base, we have to take that in consideration. So there really is also a thing that we should be adding to this. This is the number of H pluses and the number of OH minuses. In this case, it's not going to be significant because we're dealing with only one H plus and one OH minus, but should we have an acid such as sulfuric acid, H2SO4, that number here would have to be a 2 then. Or if we were dealing with a a base like calcium hydroxide, CaOH2. We'd have 2 hydroxides, so we'd have to have a 2 over here. So we have to pay attention to that when we're doing this problem, or this type of problem. In this case, again, it's only 1. So we go back up to our question here. It says that we have 35 milliliters of HNO3, HNO3 being our acid. So that's going to be my volume of my acid, 35.0 milliliters. They tell us then after 30 milliliters of NaOH, so that's the volume of my base. We have 30 milliliters of my base. They give you the molarity of the base. They tell you that it's 0.15 molar, so 0.15 molar. And the question is saying, or asking for the concentration or the molarity of our HNO3. So M sub A is our unknown. And that's all you have to do. You don't have to solve it. You could, that would be fine, but you don't have to. You just have to show the correct numerical setup. Okay. Question 31. In the space below, show the correct numerical setup for calculating the number of moles of NaNO3, given the gram formula mass is 85, used to make the unsaturated solution. Now, if you don't know or remember how to do factor label, which is how we showed you to do mole calculations, you could always just go to your reference tables where they tell you the number of moles is equal to your given mass over your GFM. They've provided you with the GFM, and they have given you a mass. So to calculate moles, it would be very easy using this formula. I'm going to do this by doing our factor label because that is how we were taught in our classes to do this, which is setting up our given over 1, which is 20.0 grams of your sodium nitrate. And then we just multiply by conversion factors being those things that are equal to 1. And we know that for every 85 grams of NaNO3, it is equal to 1 mole of NaNO3. So if these are equivalent values, then it's just like multiplying by 1. And because we have grams on top and we're multiplying here, we want grams to be canceled. We're going to put the 85.0 grams of NaNO3 on the bottom so that my grams of NaNO3 cancel. And I put my 1 mole of NaNO3 on top, and then I can solve. But again, I don't have to solve because it says to just show the correct numerical setup. Now, sometimes it's a really good idea to solve because if you did solve this and you did it the wrong way, lights are shutting off. You do this the wrong way and you flip this, you'll get a really big number. And we should see here that 20 grams is less than the 85, so we have less than a mole, so we should get a number less than 1. And if you don't get a number less than 1, then you have not drawn your correct numerical setup. All right, number 32, determine the minimum mass of NaNO3 that must be added to this unsaturated solution to make a saturated solution at 20 degrees Celsius. Okay, so we hear this saturated, unsaturated. The first thing you should be thinking is, I got to get to table G. Table G being our solubility curves at standard pressure. Okay, and you'll see here we have NaNO3 right here at the top. Okay, so they give us a temperature. So our temperature is at 20 degrees. So we're here at 20 degrees. So I'm not going to be able to show the whole thing in here based on the phone. So we're going to go up, and saturated is at around maybe 87, 88 grams, okay? So we're just gonna jot that number down. So I am saturated at 88 grams. Now notice that this is for 100 grams of water, and that's what they have here is 100 grams of water. That's important to recognize because if they had 200 grams of water, we'd be able to put in twice the amount, or in this case, 176 grams. But we're in 100 grams of water, which matches up exactly with our graph, so we don't have to do any type of adjustment of numbers. They tell us that we have 20 grams already in here. So if I can put a max of 88 in, that's my max, and I already have 20, then I need to subtract those numbers to determine that I can or need to put in 68 more grams of NaNO3 to get this to saturated. So like I said, we already have 20 in there, 88 saturates it, so I need to add another 68 grams to get up to that 88 grams if I'm starting with 20. Number 33, identify one process that can be used to recover the NaNO3 from the unsaturated solution. So anything that is dissolved, and so we're talking about a solution here. So if it's dissolved, you cannot use filtration. So filtration is not an option here. There's a couple things you can do. We just got to get rid of the water. So when we evaporate water, it does not take the salt with it. So we can use evaporation. We could use boiling. And you could even use, I guess, distillation, although that would be pretty overkill. But would be an acceptable response. Okay. Compare the entropy of 30 grams of solid KNO3 at 20 degrees with the entropy of 30 grams of KNO3 dissolved in 100 grams of water. So I guess to answer this question, you really need to know what entropy is. Entropy is disorder or randomness. So the question is, what's more random? KNO3 as a solid or KNO3 as a aqueous solution? So the answer to that is, first off, aqueous solutions are, the particles are moving around more randomly. And also with KNO3, because it's a salt, it's breaking apart. And so it's becoming two particles, a K plus ion and an NO3 minus ion in solution. So the solid locked together and not moving around, the aqueous split apart, moving around, the entropy is much greater inside a dissolved KNO3 than it is in a solid KNO3. So we can say that KNO3 aqueous has more entropy than KNO3 solid. Okay. Number 35. Explain why the total thermal energy of a sample containing 22.2 grams of NaNO3 dissolved in 200 grams of water at 20 degrees Celsius is greater than the total thermal energy of a sample of 11.1 grams of NaNO3 dissolved in 100 grams of water at 20 degrees Celsius. Okay, so this is kind of an interesting question that, usually talks about temperature and average kinetic energy, but they're talking about total thermal energy. So really our focus here are these numbers of mass, okay? Because we have more mass, we have a larger sample, it means we have more particles, and those particles all, if we're adding up the energy that each of those particles have, because there's twice as many particles, there's going to be twice as much thermal energy. So more mass, which is due to more particles, will contain more energy at the same temperature. It's kind of like if you thought about, if I was trying to warm up a glass of water versus, like, 'tis the season for swimming, a pool full of water, it would take a lot more energy to warm up that pool full of water. But hence, it has a lot more energy at the end. So all that water would end up overall having more energy. Obviously, all that energy being added and taking a longer period of time because it takes so long for it to heat up versus just a glass of water. So the more mass we have, the more energy that would be in there at the same temperature. Okay, number 36. Compare the boiling point of NaNO3 solution at standard pressure to the boiling point of water at standard pressure. Again, this is colligative properties. We just went over one earlier about the same thing. So compare the boiling point of NaNO3 solution. So again, if this is my boiling point here, and this is my freezing point here, when we're talking about pure substances like water, they're going to be boiling point for water 100 degrees and freezing point is going to be 0 degrees Celsius. But when we add a solution, if it's going to be aqueous with something in it, a solid salt, we're going to notice the boiling point goes up and the freezing point will go down. So if we're comparing the boiling points, again, this is a boiling point elevation. So the boiling point of NaNO3 solution is higher than pure water. Okay, down to question number 37. It says, in the space in your answer booklet, draw the structural formula for 2,2,4-trimethylpentane. Okay, so when we're drawing organic compounds, we should focus on the tail end. We should focus on the parent chain. So we're going to start off with 5 carbons. So pent, going back to our reference table, is always able to help us out a little bit. We have a table P right here. Hold on, I gotta adjust my phone here. Okay, we have a table P that gives us prefixes, and the pent standing for 5, so that tells us how many carbons it's going to have. And then the ane at the end correlates to this table Q. Anes have all single bonds. If it was an ene, it would have a double bond, and ine, it would have a triple bond, and with a pent, it would actually have to give us a number to tell us where that double bond or triple bond was. But in this case, it's an ane, and so we just have 5 carbons, pent, all singly bonded ane. And then it tells us 2,2,4-trimethyl. So that's meth, going back to here. Meth tells us that we have 1 carbon. So this is telling us that we have 1 carbon branches on the second, and the fourth. Tri, telling us that we should have 3 numbers here, so it's 3 different methyl groups. So we number our carbons 1, 2, 3, 4, 5. So on the second one, we have a meth, a 1 carbon chain. On the second one, we have a meth, again, a 1 carbon chain. And on the fourth, 1, 2, 3, 4, we have another meth carbon chain. You should fill these up with hydrogens. So I don't want you to forget these lines that show us that you know how many carbons can be allowed for that. And then you don't have to draw the hydrogens. You can just put the lines. Any line is assumed that there is a hydrogen on the end. But you do need to put those hydrogens in there. Number 38, explain in terms of arrangement of particles why the entropy of gasoline vapor is greater than the entropy of liquid gasoline. So we just talked about entropy being disorder or randomness. So if you're thinking about what's going to be more random, a liquid that's contained to a container or whatever, as compared to a vapor that is able to move around and occupy either the entire container or the space, the entire space that's around it. Vapor particles are moving around much more. So you would just say that gasoline vapor has higher entropy than gasoline liquid. Okay. Vapors are able to move around more freely. They're further apart. They're moving faster, so they would be more random. All right, last 2 questions. In the space provided in your answer booklet, draw the structural formula for diethyl ether. Okay, so I'm going to draw this one down here just because I don't have a lot of room up there. So you got to know what an ether looks like. You might not have memorized them. In fact, you probably haven't. But in our reference tables, we have examples of ethers and esters and aldehydes and ketones and organic acids, and they're all located right here. Hopefully when you see the ether word, you're thinking organic compounds anyways. And the ether functional group is an oxygen that basically splits 2 carbon chains. They'll list the carbon chains. Here we have methyl ethyl ether, actually supposed to be named ethyl methyl ether so that it's in alphabetical order. But regardless of that, they're going to give you those two groups before they use the word ether. And basically that just means that methyl, a 1 carbon chain, goes on one side, and an ethyl, a 2 carbon chain, ethyl, coming from here, we have our F for 2. So that's why we see here this 1 carbon chain, then an oxygen, then a 2 carbon chain. So with these condensed structural formulas. But this one here is diethyl ether. So they're telling you you have 2 diethyls that are part of this ether. Remembering that the ether is this oxygen that splits the carbon chains. In this case, ethyls. Again, we go to our reference tables, table P, eth meaning 2. We have two carbon chains being split by the oxygen. So this is an ethyl and an ethyl that makes a diethyl, and this oxygen that splits them makes the ether. Again, we don't want to forget our carbon or hydrogens that have to be attached to our carbon. And the last question, question number 40, says, in the space in the answer booklet, draw the structural formula for an alcohol that is an isomer of diethyl ether. So we need to draw an alcohol. Now an alcohol, different than an ether, you'll see that this functional group is an oxygen or a hydroxyl group, so an OH group. And it doesn't have to be on the end, but it has to be on a carbon chain, and it doesn't split. It's on a carbon, it's not between carbons. So that's kind of the focus. So there are a lot of different varieties of alcohols that we could draw here. I shouldn't say a lot, but there's a couple. But what we have to focus on is that we need to have a straight chain, or I should say we need to have carbons that are attached to one another. We can't split them with an oxygen. And you can put the oxygen on the end and fill up. You could put the hydroxyl group on the second carbon. You could make a branched chain hydrocarbon and then put the OH group here, or you could even put it here and they would be different. So there are a lot of different things you could do. Probably the easiest one would be just a straight chain carbon, 4 carbon chain with the OH group on the end. Now this is an isomer because if you look at this formula, this is C4H, count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then an O. And if we look at this, we also have C4, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and 1 oxygen. Now this typically wouldn't be written like this, but it is the same formula if we just kind of break it down to its basic elements, and therefore an isomer of that particular ether. All right, so that's it. If you watch the video and you have questions and you've done this before, Monday night, so the day before the exam, please come on in and ask questions on Monday or tomorrow on Friday. And that should be it. Good luck. You guys are going to be great. And if I don't see you or talk to you, enjoy your summer. Good luck.